Hey guys, welcome back to another video. In this video, we're going to be talking about electric field strength in uniform fields. That is, over here, the electric field strength does not change with different position. Unlike spherical charges or point charges where the fields are radial. That is, if you have a positive charge, the fields are radial. Meaning, as you move away from the charge, notice that the arrowheads are more spread out, right? The fields are more spread out. What that means is the strength of the charge to, let's say, pull another charge, let's say, negative charge, decreases with increasing distance or increasing separation between them. Therefore, the electric fields, the pulling force or pushing force decreases with increased separation. And it is the decrease is proportional to 1 by r squared, right? So in case of point charges, the electric field strength is not constant. It is called non-uniform. The fields are radial. In our case, in uniform fields, you're going to notice, let's say, in gravitational fields, you probably have heard of radial and non-radial field lines, that is uniform and non-uniform field lines. In that case, you'll notice that near the Earth's surface where the curve is so negligible, you can consider it to be almost straight, which is why near the Earth's surface, the G, gravitational, the gravity is constant, and you can use mgh for small changes in altitude to find the change in, potential energy, change in gravitational potential energy. You can use that formula because the G is constant near the Earth's surface. And why is it constant? In that case, it was because the field lines were almost uniform. The variance is so negligible that you don't consider it, right? In comparison to Earth's size. Okay, so in this case as well, even though anything in this universe is not exactly uniform, we can consider certain things to be uniform because the change, the variance might be very negligible. So in this case, we can work with charged plates to establish uniform fields. How do we do that? Let's say you have a positively charged plate and a negatively charged plate. Over here, what happens is it's going to form field lines. It's going to exert a force on any charged particle that enters this region of space because it has established field lines which goes from the positive side to the negative side, right? Okay, so in this case, if let's say we put in a positive charge, what's going to happen is this side is going to repel the positive charge and this side is going to attract the positive charge. So as a result, it establishes a potential difference between the charged plate. It establishes a potential difference between the charged plate that can be experienced by any charge, any point charge can experience that potential difference. And you can also see that through experiments with, let's say, small charged particles, be it, let's say, any sort of cloth or any sort of material that you can charge up, and you create two charged plates, one positively and one negatively charged. Or you can do another thing. You can earth one side, let's say 0 potential difference, and the other is, let's say, positively charged. Even then, it creates an electric field. So you can release the cloth or whatever you have charged up, and you're going to see the particle is going to follow an arc, a parabola. And that is due to the force being exerted on the particle. So what we understand from this is the field, the region of space, throughout the space, there is a force acting. And what we know of is, and what we're going to be talking about over here, that the electric field strength through that region is constant, is the same. Why? Because the field itself is uniform. The field is uniform. So due to the uniform field, granted you already have an uniform field, you're going to have the same electric field strength at any position. That is over here, or over here. The electric field strength is going to be the same. What that means is if you have 1 coulomb of positive charge over here, experiences, let's say, 2 Newton. 1 coulomb of charge over here experiences 2 Newton as well. So the force experienced is same throughout. That is the main idea. Okay, since that is the case, we also can work with a much simpler formula to find out the electric field strength. Since it's constant, therefore, we can use del V by del R, where V is the potential difference and del R is the separation between the charged plates. Now, how we get this formula, you have to watch the previous video. And over there, we talk about In short, what we do is we talk about differentiating electric potential to get electric fields. And how does that work? Electric fields, and if you integrate, you're going to get electric potential, right? Because if you integrate a force and distance curve, you get work done. Similarly, for electric fields, if you integrate the force and the separation or the distance, you're going to get electric potential. The work done per unit charge is electric potential. Similarly, if you differentiate electric potential, the reverse operation, you're going to get electric fields. If you carry out the same thing and write the formula down, you're going to see that electric field strength is equal to the negative gradient of the potential curve. What does that mean? That the gradient at any point is going to give you the magnitude of electric field strength. Now, don't get confused by this negative sign. This negative sign is nothing but a sense of direction. It's denoting the direction of the nature of the charge. What does that mean? So let's say you have a positive charge. What is this? What is the nature of the charge? Positiveness, right? Positive. So how can we prove that the negative sign really gives you the right answer every single time? So to prove that, what we do is, let's say we're taking right-hand side as positive, right? Taking right-hand side as positive. If you find the gradient over here, you're going to notice that it's a negative gradient. Let's say minus 2 volt per meter. That is your gradient. Now, notice that the real formula is negative of the del V by del R. Over here, your gradient is itself negative 2. So this negative and this negative gets cancelled out. As a result, you're left with positive 2. And does that match with the nature of the charge you started off with? You started off with a positive charge, right? So your final answer was positive 2. So it does match. Because positive charges have a positive electric potential, because if you bring a positive charge in its vicinity, it's going to be repelled. So in that case, due to repulsion, we know repulsion is equals to positive electric potential, right? And why that is the case, it's up there in some other video. And for negative charges, again, if we carry out the same process and you find the gradient, you're going to notice the gradient is actually positive this time. So positive 2. And if you apply that in the formula minus del V by del R, you're going to see the final answer is minus and positive. The resultant is negative. It is negative 2. What does that mean? It is negative in nature, meaning it is a negative charge. So it is indeed a negative charge, meaning the forces are attractive. If you bring a positive charge in its vicinity, it's going to attract, which is why that means it is a negative charge. So your negative sign in front of del V by del R is just denoting, it's just going to help you understand whether or not it's a positive charge or negative charge. That's it, nothing else. Now, in this case, we can use this formula del V by del R directly. We don't need to find the gradient of any sort. Why did we need to find the gradient in the previous case? Because we were working with point charges, which had forces, electric field strength, which varied at every different position. So it varied, force by distance, varied at different position, right? That is why you need to find out the gradient of the potential curve to find the electric fields and the force at any given distance. It was not constant. So you needed to find out separately for every single position by the derivative, right? So that is the main difference over here, that over there, it was not constant. The field strength was not constant. You need to find out the field strength for every single position by the differentiation process. Over here, you don't need to do that. Why? Because the electric field strength is constant, which is why you can directly apply this formula, del V, the voltage across and the distance in between. If you divide both, you're going to get the electric field strength, which is constant throughout. So electric field strength over here is like, let's say you have voltage on this axis and distance over here, and we're finding out the change in voltage or electric potential at any given position between, let's say, these two charged plates. One, let's say, has 0 volt on it. The other, let's say, has 24 volts on it. So this is positively charged. So the charge, the voltage in between is 24. So on the plate that is grounded, it's going to have 0 volt. At the midpoint, it's going to have 12 volt. And over here, on the charged plate, it's going to be 24 volts. So this is your typical voltage potential difference curve between two charged plates. Now, I need to mention one thing, that is, over here I used a plate that is grounded or has 0 volt. Why did I do that? Because, I mean, as far as I understand, as far as I know, I can't really use this example to describe it. That is because at the middle of these two charged plates, you're going to see that the potential is actually 0. So let's say you have two charged plates, one positive and one negative, and the potential difference is 24. So logically, at the middle, it's supposed to be 12 volt, right? Because it's supposed to increase from 0 to 24. Or, I mean, because the potential difference between is 24. So at the middle, it's supposed to be half of that, right? But it does not really happen. As far as I understand, I might be wrong. So if I'm wrong, do correct me down there. But in case of, two equally oppositely charged plates, in the middle, it's supposed to be 0 volt, right? And in that case, you can't really use this formula because, so let's say if the distance is 2 meters and the voltage is 24 overall, the potential difference. So if you want to find out, I mean, from this information, you can find out the electric field strength. So 24 by the separation 2 is going to give you 12, which is force per coulomb, right? That is your electric field strength. So logically, at the middle, 12 times 1, that is 1 meters, it's supposed to give you 12 volts, but that is not the case, which is why I'm not using this example. Because in case of two oppositely charged plates at the middle, as far as I know, it's supposed to be 0. The volt is supposed to be 0. But that is also why I'm using this example where one is grounded, meaning has 0 volt, and the other is, let's say, 24 volt. In that case, you can use this formula and have no problem. And you're also going to see that almost all question papers are going to use this situation where one plate has 0 volt, the other has any amount of other charge, resulting in an overall potential difference. And in these cases, you can draw this curve and say that the potential increases from 0 to 24 on this plate. So you can use this formula. But yeah, that was a bit of excess information, unnecessary. But the main thing is you need to understand you have to use del V by del D or del R, whatever you want to call it, the potential difference by the separation between the plates to find the electric field strength, and that electric field strength is going to be constant throughout the region. That's the main idea. Okay, you can't use this for point charges because, again, field strength is not equal at every position. That's what I've mentioned over here, which is why you can't use this for point charges. And you also can't just assume that, let's say you have 2 point charges, one positive, one negative, and let's say the volt between them is, let's say, 24. The potential difference between them is 24. The separation T. You can't just write 24 by 2 and say the electric field strength is 12 because it is not constant. It is different at every position. So you cannot do that. Okay, that is the main point. And over here, I've explained on that. So when in uniform fields, the electric field strength is the same at any distance, as said before. Again, that's why it is called uniform. That is also why we can use del V by del R, meaning if we change either, this is the important part, if we change the voltage across the plates, or let's say we change the separation, either of those is going to change your electric field strength. So let's say initially it was 24 volt and 2 meters across, resulting in 12 force per coulomb. Now it's going to, let's say, increase to 30 volt with the same separation, 2. Now it's going to give you 15 newtons per coulomb, right? So you can change either and toggle with the electric field strength, right? For radial fields, the point charges, the electric field strength is different at every distances, which is why we use E is equals to KQ by R square, because yes, the field strength is different at every position. Okay, so that's the main idea of electric field strength in uniform fields. Hopefully this video helped, and see you in the next one.